The Koch snowflake is named after the Swedish mathematician Helge von Koch, who in 1904 described a curve with very special properties. The word snowflake is often used to refer to two slightly different versions. There is the filled snowflake, shown here, and there is also the boundary, sometimes referred to as the snowflake curve. We will demonstrate 3 ways to construct the snowflake curve using different techniques for drawing the Koch curve, and also 4 techniques to construct the filled snowflake. The first method is the one often used to draw the snowflake curve based on Koch's 1904 paper. This paper described the geometric construction of a continuous curve that had no tangents, a curve that later became known as the Koch curve. To construct the Koch curve, start with a line segment P1. Remove the middle third of the line segment and replace it with the 2 edges of an equilateral triangle. This operation creates what Koch called the polygonal line P2 that consists of 4 new segments of equal length. The same operation is now applied on each of these segments by removing the middle thirds and replacing them with 2 edges of the corresponding equilateral triangle. By applying this operation on each of these new segments and continuing in the same manner indefinitely, one obtains an infinite sequence Pn of polygonal lines. As n increases, the sides of the new equilateral triangles that are added will get so small that you may not be able to see the differences on the screen unless you zoom into an image. The Koch curve is then the limit of this sequence of polygonal lines as n goes to infinity. But all we can draw with a computer is just a good approximation for a sufficiently large value of n. The snowflake curve can now be formed by starting with an equilateral triangle S1 and iterating the construction of Koch curves along each of the 3 sides of the triangle. This produces a sequence Sn of polygonal lines that will converge to the snowflake curve as n goes to infinity. There is also another way to draw the snowflake curve using Koch curves. Notice that we can draw a regular hexagon around the outside of the snowflake curve. If we construct Koch curves inside the hexagon along each of the 6 edges, then in the limit, these 6 Koch curves will coincide with the 3 original Koch curves from the equilateral triangle. So the snowflake curve can be constructed using either an equilateral triangle with 3 Koch curves drawn outward, or with a regular hexagon using 6 Koch curves drawn inward. The next method is based on an alternative construction of the Koch curve as a Trema fractal, a type of fractal generated by recursively removing parts of a geometric figure. It begins with an isosceles triangle L0 having angles of 30 and 120 degrees. This triangle can be subdivided into 3 smaller triangles, an equilateral triangle, and 2 isosceles triangles that are similar to L0. The trema to be removed is the equilateral triangle, producing the image L1. Now the process is repeated indefinitely. At each iteration, each remaining isosceles triangle is divided into 3 pieces, and then the equilateral triangle is removed. Here we show the first 10 iterations. You may no longer see the many triangles formed during the iterations, but they are still there. This produces a sequence Ln of approximations, and the limit as n goes to infinity is the Koch curve. Now to construct the snowflake curve, we place 3 copies of an isosceles triangle around the sides of an equilateral triangle. An approximation of the snowflake curve can now be obtained by iterating the trema process on each of these copies a sufficient number of times. The last method for the construction of the snowflake curve uses a Lindenmayer system, or L system for short. Aristid Lindenmayer was a Hungarian biologist and botanist who in 1968 developed a system to mathematically model the development of plants. It was later adapted to the Logo programming language and to turtle graphics for drawing images on a computer screen. We will describe how an L system can be used to draw the Koch curve using turtle graphics. An L system consists of an alphabet, an initial axiom, 1 or more production rules, and an angle. We start with the axiom string, which we label C1. If we place a turtle at a starting point, then the F would represent a forward step of unit length by the turtle. The result is the polygonal line P1 from the construction of the Koch curve. For the first iteration, replace the F in C1 according to the production rule to get the string C2, as shown here. The string C2 represents the path that the turtle is to walk for this iteration. The first F says move forward 1 unit. The plus sign means turn left 60 degrees. The next F again moves the turtle forward 1 unit. The two minus signs indicate 2 right turns of 60 degrees, followed by another move forward, followed by another left turn of 60 degrees, and then a final move forward. The result is the polygonal line P2. Notice that we have scaled the length of the turtle's forward motion by 1/3, so that the endpoint is the same as with the string C1. The next iteration replaces each of the letters F in C2 according to the production rule to get the string C3. What is the path of the turtle resulting from the interpretation of the string C3? We again scale the length of the turtle's movement by another 1/3 to keep the endpoint of the walk the same. The result is the polygonal line P3. The L system iteration can be extended indefinitely to create longer and longer strings. Since each CN begins with the previous string, it makes sense to express the Koch curve as the infinite string that is obtained as each finite string CN is extended to the limit. But just as we can only draw a finite approximation to the Koch curve using polygonal lines, we can only draw an approximation using a finite number of iterations of the L system. Here is a good approximation to the Koch curve represented by the string C6, a string with 2,388 symbols and representing 1,024 forward steps by the turtle. We can now use this L system with a few adjustments to construct the snowflake curve. First, we change the axiom to describe an equilateral triangle, and then we also switch the plus and minus signs in the production rule so that the Koch curves are drawn outward from the triangle. We can see how the axiom string S1 produces an equilateral triangle. The first iteration of the L system replaces each of the letters F in the axiom according to the revised production rule to produce the string S2. If the turtle is moved according to string S2, the result will be the first step in constructing Koch curves outward along each of the 3 sides of the triangle. The L system iteration can now be extended indefinitely to create longer and longer strings, each giving a better approximation to the snowflake curve. Here is the result using 5 iterations, with each Koch curve drawn in a different color. We turn our attention now to the filled Koch snowflake, using a method involving triangles to construct the snowflake. Start with an equilateral triangle T0. Scale the triangle by 1/3 and add 3 copies around the edges of T0 so that they face outward. This produces the image T1. Next, scale by another 1/3 and add 12 copies around the sides of T1, again facing outward. This produces the image T2. Continue constructing more images in the same way. Each subsequent iteration will scale the initial triangle by another factor of 1/3 and increase the number of scaled copies by a factor of 4. This process is continued indefinitely to produce a sequence Tn of images. As n increases, the new scaled copies that are added will get so small that you will not be able to discern the differences on the screen unless you zoom into an image, as we have done with the earlier methods. An infinite sequence of increasing images is constructed this way, and the filled Koch snowflake is then the limit of this sequence as n goes to infinity. We can also construct the snowflake by removing triangles from a regular hexagon. Label the hexagon H0. Construct an equilateral triangle with the same width as a side of the hexagon. Scale the triangle by 1/3 and place 6 copies on the sides of H0 so that they face into the interior of H0. Remove these triangular regions from the hexagon to produce the image H1. Next, scale the triangle again by 1/3 and place 24 copies around the sides of H1, facing into the interior as before. Remove these triangular regions from H1 to create the image H2. For the third iteration, scale the triangle by another 1/3 and place 96 copies around the sides of H2. Then remove these regions to get the image H3. Continue constructing more images in the same way. Each subsequent iteration will scale the previous triangle by another factor of 1/3 and increase the number of copies by a factor of 4 to produce the image Hn. An infinite sequence of decreasing images is constructed this way, and the Koch snowflake is then the limit of this sequence as n goes to infinity. So what happens if we do both constructions at the same time? Consider the visible brown regions that are inside the hexagon but outside the triangle. These brown regions correspond to the same isosceles triangles that we encountered when constructing the snowflake curve using the Trema method. As n increases, each iteration in the construction of the approximations Tn and Hn will correspond to another step in a Trema removal from the brown isosceles triangles. So as the Tn blue region expands outward in constructing the filled snowflake, the brown regions will shrink inward and converge to the snowflake curve as n goes to infinity, thereby becoming the boundary for the snowflake. The next method was first described by Benoit Mandelbrot. It makes use of an initiator, which is a starting shape, and a generator, which is a collection of scaled copies of the initiator. Start with a directed line segment and two special endpoints as the initiator. Construct an equilateral triangle with the line segment as the base, and with the triangle placed to the left of the segment when moving in the direction indicated by the arrow. Now add a copy of the triangle rotated by 180 degrees to form an interior hexagon. The two triangles intersect at the 6 vertices of this hexagon. We now construct the generator by connecting this network of points with the following 7 directed line segments, where the arrows indicate the direction of each segment. The path of the generator starts and ends with the 2 special endpoints of the initiator. Notice that each of the 6 smaller segments in the generator lies along the base of an equilateral triangle that is oriented to the left of the segment when walking along the segment in the direction of the arrow. The longer segment also lies along the base of an equilateral triangle inscribed inside the hexagon. The iteration construction starts by replacing each of the line segments in the generator with a scaled version of the generator, such that the 2 special endpoints are mapped onto the ends of each line segment, and the scale generator is placed to the left with respect to the direction of the oriented segment. Notice how each copy of the generator now lies inside the corresponding equilateral triangle. This new path also starts and ends at the 2 special endpoints. We can now continue iterating the construction as many times as desired by replacing each line segment in the current path with a scaled version of the generator, always placing the scaled version to the left of the oriented segment. Let's see what this looks like if we remove the arrows and points and only show the path superimposed on top of the Koch snowflake. As we zoom in on the path, notice how it bends and turns. But the path will never cross or intersect itself. As we draw more and more iterations, each new path will continue to fill more of the Koch snowflake, all the while never intersecting itself. Here is the next iteration. The limit of these paths as the number of iterations goes to infinity is a space-filling curve whose range is the Koch snowflake. In 1981, John Hutchinson introduced a technique for creating self-similar fractals using a set of contraction mappings in the plane. These sets became known as iterated function systems. Our iterated function system will consist of 7 affine transformations involving the operations of scaling, rotation, and translation in the plane. Choose any initial compact set, S0. Here we will use a hexagon centered at the origin. Now apply each of the functions in the IFS to this initial set. The first function scales S0 by 1 over root 3, then rotates by 30 degrees. The remaining 6 functions will each scale the initial set by 1/3 and then translate by the indicated amount. We show the result of each function applied to S0 in a different color. The union of these 7 pieces now constitutes a new set S1. For the second iteration, apply each of the functions in the IFS to the set S1. The same scaling, rotation, and translations will transform S1 into 7 new pieces. The union of these 7 pieces now forms the set S2. Keep repeating the construction by applying each of the functions in the IFS to the current set and taking the union to get the next set. Continue the iteration indefinitely to produce a sequence Sn of compact sets that will converge to a limit as n goes to infinity. This limit set is called the attractor for the iterated function system, and for this particular IFS, the attractor is the Koch snowflake. We could have started with any compact set, and the sequence of iterations would still converge to the Koch snowflake. Even if the initial set was as complicated as, for example, a turtle, what happens if we apply the IFS to this initial set? Here is the first iteration of the IFS applied to the turtle. As with the hexagon, we will show the effect of each transformation on the initial set. You can already see how the 7 pieces of S1 are starting to fill the snowflake. The second iteration will get even closer to the attractor. Now let's do a few more iterations, but show the result of each iteration without the intermediate steps. So after 5 iterations, the turtle has become a good approximation to the Koch snowflake. Let's see what happens if the iterated function system is applied to the actual snowflake. In this case, no limit is needed. The snowflake is the fixed point for the IFS, which means that the snowflake is the unique non-empty compact set, for which the IFS maps the snowflake onto itself as a collection of smaller copies, as we see demonstrated here. In other words, the snowflake is the union of 7 self-similar copies of itself, 1 copy scaled by 1 over root 3, and the other 6 copies scaled by 1/3. Our final method uses 2 versions of the chaos game. This version of the chaos game is also known as the random iteration algorithm. We use the same 7 functions as with the iterated function system from the previous method, but now we associate with each function a probability. The first function has a larger probability because it scales by a larger value than the other 6 functions. Start by choosing an initial point x0 in the snowflake. We will take the origin for this example. Now choose a function at random based on the probability distribution. Suppose it is function 4. Apply function 4 to the point x0 to get a new point x1, which is then plotted. Now choose another function at random. Suppose it is function 6. Apply function 6 to the point x1 to get a new point x2, and then plot this point. Continue selecting functions at random and using the chosen function to compute the next point. These points are called the orbit of the initial seed x0. They are all guaranteed to be points in the snowflake because the snowflake is the fixed point for the iterated function system as we saw previously. So a point that starts in the snowflake will stay in the snowflake with each iteration. Here we see the first 15 points in the orbit of the initial seed. They just look like a group of randomly scattered points. But what happens if we repeat the iteration 5,000 times? Now we see how the points are filling the Koch snowflake. Notice that the red region has more points and is larger, since the first function has a greater chance of being chosen at each iteration. To get a better approximation, let's do the iteration 500,000 times. But now, instead of coloring each point based on which function has been randomly chosen, we will use the technique of color stealing from the input image shown here. Set the scale for this input image to be the same as the scale used for the snowflake. Now run the chaos game on both the input image and the snowflake simultaneously. Each time a random function is chosen for the next iteration of the snowflake, that same function is also used to draw the corresponding point on top of the input image. The point computed for the snowflake is then plotted using the same color as the point from the image. We say that the iterated function system has stolen the color from the input image. We see that as more and more iterations are taken, the points are forming a very good approximation to the snowflake, and the colors in the snowflake mirror the colors in this kaleidoscope input image. And after 2 million iterations, we have an even better image of the snowflake with the stolen colors. Here is another way to play the chaos game for the Koch snowflake. Draw a regular hexagon and label the 6 vertices and the center of the hexagon. The rules of the game are given in terms of these 7 special points. Start with a random point near the center of the hexagon. Now roll the die. Here we have rolled a 2, so we move 2/3 of the distance to vertex 2. Now roll the die again. We rolled an 8, so we move 0.4226 of the distance to the center, then rotate 30 degrees around the center. Now continue playing the game to plot a few more points. Now that we see how the game is played, let's play 3,000 times. The 7 special points associated with the hexagon are actually the fixed points of the 7 functions from the iterated function system in the previous method, so the fixed point algorithm is really just a different way to describe the random iteration algorithm. It is therefore not surprising that the points plotted from this chaos game are filling the snowflake, just as they did before. If we continue the game for another 45,000 plays, we get an even better view of the snowflake, shown here after every 3,000 rolls of the die. And just as with the random iteration algorithm, we can use the technique of color stealing by playing the chaos game simultaneously on both a suitable input image and the snowflake, as, for example, with this image. We have now seen 7 ways to construct the Koch snowflake, but most likely none of them were ever used by Koch himself. While the snowflake is clearly based on the curve that Koch introduced in 1904, the image of the snowflake curve does not appear in any of Koch's mathematical papers. To find out more, check the description for a link to an article that attempts to answer the question, who invented the von Koch snowflake curve?